All right, great. Thank you very much. Thanks for the invitation to speak at this workshop, and thank you to the organizers. Yeah, so I'm in the somewhat fortunate position here of speaking after Jonathan's talk earlier, where he sort of, in some sense, laid out the meat and potatoes of actually what the algorithms are in my talk. So I will certainly still recap for anybody who is just joining now, but at least now I can talk a little bit more about our interesting results at the end. But yeah, so anyway, I'm going to be talking about using deep learning weather prediction models to make global forecasts at the subseasonal time range using large ensembles. So this is work that I did with my for my PhD with my advisor Dale Duran and our collaborator Rich Caruana at Microsoft Research. So as we all know, numerical weather prediction has undergone what has been aptly called a quiet revolution in the last few decades, where forecast accuracy has increased greatly due to advances in numerical methods, large networks of data collection, and of course, supercomputing power. But one of the questions many of us here are asking is it possible to stretch these improvements even further by applying modern machine learning techniques? And in fact, there's been an explosion in the application of machine learning in meteorology, specifically for weather forecasting aspects such as post-processing NWP models, identifying extreme weather events, and doing things such as replacing physical parameterizations inside NWP models with more computationally efficient data-driven solutions, such as neural networks. But the question that our group has been asking specifically is, what if we could use machines to predict the evolution of the entire atmosphere? So the earlier talk presented the weather bench dataset, which is providing very specific tasks to target development of models that can actually do emulation, essentially, of numerical weather prediction models, or actually model replacement with machine learning methods. So this is what we are looking at here. So we developed our deep learning weather prediction model, which uses convolutional neural networks on a Cubesphere grid. And so while we are essentially replacing an NWP model, there are some important caveats to note here. The first is that we only forecast a few variables, so this is hardly a complete weather forecast. And the second is that the training data, including the data that's used in the weather bench benchmark dataset, comes from the Era 5 reanalysis, which is actually dependent on state-of-the-art models and data assimilation. So these techniques are, at the moment, not completely free of all the advances that have been made in NWP. Nevertheless, so let's go into some of the details about how our algorithm works to produce weather forecasts. So similar to the talk earlier, our model uses an iterative time-stepping method so that we can essentially replicate the behavior of a numerical weather prediction model and make indefinitely iterable predictions every 6 hours in the future. So our model takes as input 2 time steps, as represented by the atmospheric state vector x at some time t minus 6 hours and t. These are fed into our algorithm, aptly showed as a black box here, which then predicts the next 2 time steps at t plus 6 and t plus 12 hours. And then during the training process, this prediction is actually fed back into the algorithm containing the same weights and layers to predict the next 2 time steps, t plus 18 and t plus 24. So our algorithm is producing a state vector that has the same dimensionality as the inputs. And because we know what the weather looked like at all of these predicted timestamps, we can then minimize the loss function here using mean squared error over multiple cycles of iteratively feeding into the model to simulate its behavior in an actual indefinite iteration prediction. So this helps improve the model stability quite a bit. Of course, the algorithm that we use, we've heard a lot about convolutional neural networks, so I will keep this brief and mainly point out that as Jonathan noted earlier, that the traditional representation of atmospheric data is often on an equirectangular longitude grid, but these grids have heavy distortion near the poles, which makes them not very well suited for using convolutional neural networks, which assume translational invariance, and that the area covered by the convolutional filter will be the same no matter where it looks on the image. So the way that we address this problem is to remap all of the data offline onto a Cubesphere representation of the globe. So Cubesphere looks something like part A in this figure, and if it is flattened out to its 6 faces, part B of this figure shows an example temperature map of what the world looks like when we flatten out the faces of the cube. Now, the Cubesphere has a couple of attractive properties and a couple of disadvantages as well. So its nice properties is that it's relatively easy to come up with padding conditions around each of the individual faces, which are necessary in order to maintain the dimensionality when applying convolution operations inside a neural network. So we can pull the points from neighboring faces of the cube, like these blue and orange points, which are used to pad the edges of the green face. This does leave one point ambiguous here, which in practice we use either the blue or the orange face to fill in this point, depending on the location. But it does make things relatively easy and make sure that the entire problem is completely closed in the lateral boundary conditions. Of course, the disadvantage is that this doesn't completely eliminate distortion, and it's also not clear whether it's even appropriate to use the next face as an exact neighboring boundary condition. However, it turns out that our algorithm is able to do quite well with this and produce stable forecasts indefinitely into the future. Now, we also make a slight modification to this, which is that because the convolutional network operates on each face of the Cubesphere grid individually, we actually learn a different set of weights for the 4 equatorial faces than we do for the 2 polar faces. So this enables the model to learn the very different dynamics that it would observe in the polar faces relative to the equatorial faces. We implement our algorithm in TensorFlow, and the code is available on GitHub. This is the particular algorithm that we use relative to current state of the art. This is actually not very sophisticated, but it's a pretty standard UNet autoencoder decoder architecture. Now, in terms of the data that we use for our model, we use 6 input fields from the ERA5 reanalysis, including 500 hectopascal height and 1000 hectopascal height, thickness between 3 and 700 hectopascals, 2-meter temperature, T850, and total column water vapor as a measure of moisture. And we also prescribe the incoming solar radiation, this is theoretical max radiation, a land sea mask, and topography. And just as a quick demonstration that our model is producing realistic things and can also be iterated forward indefinitely in time, we can look at a free running 1-year forecast where the verification is shown in the middle, daily climatology is on the right, and we can see that our model forecast on the left is producing interesting wavy patterns, much like we see in the verification, instead of regressing towards a mean climatology state. And as we keep progressing further into the simulation, we are now approaching the fall and winter season. And we can see that the machine learning model with only the prescribed top of atmosphere radiation is actually able to deepen the heights around the North Pole as appropriate for the onset of the winter season. So as you can imagine, our model is certainly not as good as current state-of-the-art NWP for many reasons, but we might ask, well, what can we still do with our model? Can we possibly make a large ensemble system? Now, why would we actually bother doing that? Well, as we know, the larger the ensembles we make, the better we can sample probabilistic distributions for future forecasts. And it turns out that our DLWP model has a pretty significant computational advantage in its current iteration relative to traditional models. So you could ask how long it would take to run a 1,000 member ensemble of 1 month forecasts at about 1.5 degree resolution. And it turns out that our model can do that in 10 minutes on a single workstation with a single GPU. In contrast, using a CPU machine with a current version of the ECNWF model would take approximately 16 days to do the same task. Now, when we design an ensemble model, we need to obtain correct ensemble spread. And so we have to consider how we are going to represent model uncertainties inside our modeling framework. So in numerical weather prediction, we account for both observation uncertainty and model uncertainty. Observation uncertainty comes from perturbing initial conditions, and model uncertainty comes from techniques such as stochastically perturbed parameterization tendencies. In our machine learning model, for observation uncertainty, we do the same thing. We use different initial conditions to run the model. But to account for model uncertainty, we actually leverage the randomness that's involved in the training process via the initialization of weights and the randomness in the gradient descent optimization to retrain the model and end up with slightly different weights in the final model, which can actually form essentially what is a swapping physics model perturbation ensemble. Just as a quick summary of our ensemble system versus the current ECNWF ensemble, as you can see in terms of variables, horizontal resolution, other physics and coupled models, our technique is clearly inferior to the state of the art. But where we can make up some ground is by having a computationally efficient large ensemble, which currently we use 320 members versus the 50 members of the ECNWF. So I'm just going to go over this relatively quickly here. This is the root mean squared error in Z500 as a function of forecast lead time. And we can see that our ensemble in the green outperforms a single deterministic forecast shown in the blue of our method. But we still lag about 2 to 3 days of forecast lead time behind the state-of-the-art ECNWF ensemble. A similar story can be shown in the anomaly correlation metric, which measures skill relative to climatology. Again, our ensemble approach definitely does better than a single deterministic forecast, but still lags behind the state-of-the-art ECNWF. So even though we may not be as good as ECNWF in the medium range forecasts, where the power of a very large ensemble may really manifest is in producing longer term forecasts, such as those on the sub-seasonal to seasonal timescale. And sort of qualitatively, it's generally agreed upon that this sort of S2S time range, which falls between about 10 to 30 days, has relatively poor forecast skill because it comes inside, it's outside of the range of the predictability coming from initial conditions, but not far enough for slowly evolving components of the Earth system, such as sea surface temperature, to provide useful skill relative to simple forecasts such as persistence. And ideally, we'd like to be able to produce forecasts at a resolution of weekly averages or better in this S2S time range. Now, I will mention the caveats that we can't really expect our DLWP model to compete with the state-of-the-art because it is lacking a few important features for S2S forecasting, including an ocean model, land surface parameters such as moisture, sea ice, and very importantly, precipitation. Our current version of the model does not forecast precipitation, although we are working on our methodologies for adding this. The result of this is that we can't represent the physics of longer-term patterns such as the MJO or ENSO, which are important for S2S prediction. So let's just look really quickly at a probabilistic skill score for our ensemble. I'm going to use, in this talk, the measure of the ranked probability skill score. To compute the score, we first define 3 equally probable tersols relative to a climatology, which are categories of below, near, and above normal. The forecast probability of being in any of these categories is simply determined as the fraction of ensemble members. And then we evaluate the squared error of the forecast probability versus which category was actually observed, accounting for the ranking between the categories. Finally, the score is normalized relative to random chance prediction of 33% likelihood in each category, which is, as a result, a perfect score is 1, a higher score is better, and a negative score means that there is no skill relative to random chance. So this figure shows the scores from our DLWP ensemble and the ECMWF ensemble for forecasts average over a couple of lead times from 6 to 10 days to 8 to 14 days, week 2, all the way out to weeks 5 to 6, 20 days, 29 to 42, in terms of 850 hectopascal temperature. So as you can see, at all of the forecast lead ranges, our model has positive skill, better than random chance. And as we go to longer and longer lead times, our skill approaches that of the ECMWF ensemble, but is still a little bit behind. If we look at just points over land, however, then we can see that the gap is actually smaller between our ensemble and the ECMWF ensemble, to the point that there's within statistical 95% confidence threshold by weeks 5 to 6. It's also interesting to look at spatial maps to see of the skill to see where the model actually has predictive skill. As you can see, at week 3, most of the skill comes from the equatorial ocean, and clearly the ECMWF ensemble shown in the bottom has higher skill scores than our model. At week 4, both of the ensembles degrade slightly, but the patterns remain largely the same. Then at weeks 5 to 6, the skill does increase relative to week 4 simply by virtue of the longer averaging window. But if we look especially over land points, we can actually see that there's very little to distinguish the skill of our ensemble versus that of the state-of-the-art ECMWF ensemble. And I just want to point out one other interesting feature. This is the same skill map, but for 2-meter temperature here. As it's not very surprising to see the ECMWF ensemble performing extremely well over the ocean, since they have a coupled ocean model as well. Nevertheless, over land, our model still has positive skill scores in most regions, but it does have one important deficiency, which is over the equatorial Pacific. It actually has low skill scores because it failed to predict the onset of El Nino-like patterns in the boreal autumn. So with that, I'd like to just leave you with a few key takeaways. So we were able to produce an algorithm that made realistic and indefinitely stable global weather forecasts. We can construct an ensemble of these forecasts using the same techniques as operational ensembles for modeling uncertainty. And we were able to predict forecasts in the ES2S time range, which are not far behind the state-of-the-art ECMWF ensemble. And so with that, happy to answer any questions if we have time.